United in AI, we learn and United in AI, we learn and lead, ensuring we always stay ahead. February 2022, Russia launched a full-scale invasion of Ukraine. To support the Ukrainian tech sector, the largest AI community in Ukraine, AI House, brought together global AI experts for a charitable education project, AI for Ukraine, lectures and workshops about the latest in AI and ML in exchange for donations to Ukrainian defenders. This time, AI House teams up with one of the most powerful Ukrainian AI ML tech companies, Roosh, for AI for Ukraine Season 2, to assist Ukrainian AI talents in expanding their network, equipping them with the most current and relevant knowledge in AI and ML, and raising funds to support Ukraine. Join AI for Ukraine Season 2. Harness the opportunity to learn, network, donate, and support Ukraine.
Good evening, everyone. Welcome to the AI for Ukraine Season 2. It is the last lecture in this season. Today with you, Timur Tleberlin, me, I'm co-founder at Desti Labs. It's an agency where we develop machine learning models and solutions with AI. And today we will have a great lecture on AI in biomedical imagining, and we will talk about how computer scientists can contribute to the medical field. And today we have our guest Dmytro Fishman. Hi, Dmytro.
Hi, everyone.
Yeah. By the way, today is a special day for Dmytro. It is his birthday, so congratulations on your birthday.
Thank you, guys.
Dmytro. Yeah, and before we are waiting for the people, can you introduce yourself, a little bit about your background and where are you working now?
Yeah, sure. I actually have a whole slide dedicated to that, but long story short, I am assistant professor of artificial intelligence at the University of Tartu. This is probably not the most well-known and popular place around there. I watched your this introductory video of AI for Ukraine, and you had Joshua Benjo. This is cool. Like University of Tartu is not as known, but it's a fairly it's a strong university in Estonia, and obviously, and Estonia is now obviously has been very prominent in support of Ukraine. Thank you, Artem, for congratulations. So Estonia has probably emerged on the map when it comes to recent support of Ukraine. The country has given out everything they could, and University of Tartu is probably the strongest university in Estonia, but also Baltic states in that sense. And I'm teaching there, but I'm also doing research, and I do research exactly in biomedical imaging. Plus, I have co-founded 3 years ago, I have co-founded a company called Better Medicine. This is the company that develops and integrates AI solutions into medicine. And this is exactly what I want to talk about today.
Yeah, it's great. And where are you joining us from today?
Well, this is where I am. University of Tartu. Tartu is a small place. It's actually the second biggest city in Estonia. The first one is Tallinn. Hopefully people know that, but the second one is Tartu. It's dangerously close to bloody Russia. So we're not like, we're like Estonians generally think that by supporting Ukraine, they fight the war because they know that if something happens, the bloody Russians come for them. So we are very much into it, all of us here. Well, including Ukrainians, of course, which I am myself. So.
Yeah, it is. And by the way, as we started to talk about supporting Ukrainian defenders, you can find a little QR code on the right corner. And by going to it QR code, you can donate to the Reactive Post. It is a fund that supports our Ukrainian defenders. So feel free to do it.
Please feel free. Quite free.
It is very, very appreciated. And as I
Can we
see,
stop?
we already have a lot of people joined, so we can start our lecture today, giving the microphone to you, Dmytro.
Thank you, Timur. It's nice meeting you, and nice meeting you, all of you guys online. It's great to be here at AI House, and I'm very honored. So thank you very much for inviting me. I do understand that the topic is not, let's say, orthodox from maybe other things that have been discussed in this season and the previous season. So I'll try to make it very clear of what exactly I want to talk about. So myself being assistant professor of artificial intelligence and researcher at university, but at the same time being a co-founder of the company of a biomed tech startup, I really want to show, and my whole purpose of all these kind of uh, conversations and meetings that I have with the public is all about convincing people that have IT background or computer science background that they can make a difference when it comes to biomedical sciences and biomedical progress in medicine and biology, convincing them that they can do it. So that is going to be the purpose of my talk. I want to show you what we do at the computer science department. So I have no biology background whatsoever. I'll show you what my lab and my company does as a bunch of computer science engineers, and maybe I'll just show you a way that this is also something that you can do. I guess before we start, I just wanted to quickly say that besides what the AI House themselves, they also collect the money for the Ukrainian defenders. I have a little bit of my own agenda, which we have discussed with them as well, and they very generously allowed me to advertise this specific donation channel. This guy here on the picture is the father of my PhD student, so he is actually in the trenches protecting the land right now, and he's heading the strike crew. So these are the guys who have drones and they attack the enemy positions and they try to destroy the tanks and artillery that basically shuts the and shells the people. So basically, we are collecting money for these guys, and you can see the QR code and the link. Obviously, I would be super grateful if you could donate a little to their purpose as well. Cool. We have been through the introduction slide already. Just a quick summary. I have also graduated from Kyiv Polytechnic Institute. So I myself come from Ukraine. I'm from Kherson. This is where I grew up. And then I went to Kiev. I graduated one of the biggest universities in Kiev and went to Tartu University, Tartu Ulikol, as you can see in one of the logos here. I have done my master's and I had some exchange programs here and there. And then I started my PhD. So in 2021, I actually graduated with my PhD in bioinformatics and started off as an assistant professor and later became a co-founder of the company. All right, this is shortly about myself. Now, when I talk to people about biomedical imaging and in general medicine and the challenges that we are facing when we are studying things that happen in human bodies, it's not always apparent of what scale of the problem we're talking about. And in order to illustrate the scale, I usually ask people to think of a large number, like properly large number. And since people don't really go too far with their thinking of the large numbers, then I ask them to think of, for example, how many stars there are in our galaxy. And the answer is it's about 200 billion stars. Okay, it's a fairly decently large number. You don't want to walk the street and have this number of something in front of you. So this is a fairly large number. But it turns out that if you think about the human bodies or generally living organisms and human in particular, then, for example, average human has about 37.2 trillion cells. So it's a magnitude, several magnitude, orders of magnitude bigger than number of stars in our galaxy. And so the scale is slightly shifted here. It's the trillions of cells in each one of us that makes a difference, right? And if you think about stars, then the stars are very boring in a way. They're just a very dense, compressed, but very uniform matter. So it's not super interesting. I mean, it's definitely interesting from many different physical points of view how these kind of things come together in that way. But from the perspective of communication and the internal processes, our bodies have definitely a lot more to offer in terms of complexity. So our bodies are definitely a lot more complex objects than these kind of stars that make up our galaxy. These are trillions of cells, as we have just figured out. These trillions of cells make up tissues that in their own turn make up our organs that make us, basically. This is what we are. We are basically a collection of tissues that are made of cells. And as you can imagine, yeah, it's very, very complicated system, meaning that the cells and tissues and organs, they communicate with each other, they exchange all sorts of liquids and bacteria and many other things. And this system, as any other complex system, is to some extent has a potential to break, right? So there is a potential for the mistake, for the something going wrong. And as just one example of these things that can go wrong, you can imagine a cell, a rogue cell that starts to divide endlessly, right? It starts to divide endlessly and it starts to invade the tissue in which it has resided, which starts to essentially grow as a tumor, as a lump of tissue, which we call tumor, that has that usually grows in size, and then it basically gets this functionality that basically starts to detach itself and actually send itself to other organs and as a form of metastases, and essentially at some point it kills the host. Right. So this is the classical story of the cancer, the classical story of the cancer killing a person. Now, you here in this stream, you might wonder, so what it has to do with the people, as in the title, with the computer scientists, right? So people with the laptops, how these people with the laptops, what they have to do with the cancer story. It turned out that, the right side, the story of the cancer, this is very biological story, while people on the left side, the people with the laptops, they have been very successful in solving many different problems over the last 15 years. These include classifying hundreds of thousands of images into thousands of various categories. They have been relatively successful in taking over and reducing the amount of manual interaction that has to be provided to the car in order to drive itself. They have been relatively successful in building algorithms that can generate very realistically looking pictures, photos, art, whatnot, right? So it turns out, again, as a next surprise, that many of the problems that I have illustrated on the currently it's on my right side of the slide, they have some sort of representation that people with laptops and computer scientists like myself and many of you who are watching this know how to solve, that have been successful in solving. And I'll give you a bunch of examples throughout the talk, and I'll show you how myself and my group at university, as well as my company in industry, how do we approach these problems and what you in principle can do as well. Okay, so a couple of examples here. So let's focus on one level of this cancer story that we have gone through. And we start with cellular level, right? Microscopy images level, because that's where you can see the cells in microscopy. The thing about this is that, and why is it even important, why people care about microscopy and cells, is that when biologists, in that case, these are biologists, they are not doctors yet because they're not really talking to patients, they're talking to cells. And once they're talking to cells, they're biologists, microscopists. So when a biologist is developing a new drug against, for example, cancer, you guessed it, then they don't normally go around the town and they don't offer, random people on the streets if they want to get a short injection of their experimental vaccine against cancer. They usually do it in the lab. They grow a cell line, which is normally a cancer cell line. For example, this is the cancer cell line that you can see in the picture. This specific cell line, I think, is from the liver cancer. And they grow it in a dish, right? So they grow a cell line in a dish. And then the biologists, they develop a new drug. And once they develop a new drug, they administer this drug to the dish, to the cells. They inject the drug to the cells that they grow of this cancer cell line. And obviously what happens is that they want to learn whether the, let's say, cells reacted to this drug or they didn't. So the way how they do it is just counting the cells, right? So they just have to figure out whether cells died or didn't. And the usual way to do it is by manually drawing the cell contours and then just counting them in the algorithm. But instead, for example, my lab, we have been one of the first ones to actually build a convolutional model that would segment cells. So we were the ones to train, well, not the first ones, obviously, but we were one of the first ones to actually start properly training this kind of models such as UNet to segment those nuclei of the cell and quantify them in terms of what's their shape, what's their size, and in that way, helping biologists to understand whether their experiment worked. Okay. Now, moving on from here, this picture that I showed on the previous slide of the cell line, it's called a fluorescent image. And it's called fluorescent image because there's a lot of fluorophore in this image. These are the small chemicals that shine light when you project a certain type of wavelength, right? You can see nuclei very, very clearly here. And therefore, it's very easy for the algorithms to actually pick the signal and find the cells. Okay. There is a different type of image, which is called bright field image, which is a lot more complex than that. And the problem with the bright field image is that you can't really see the cells. Well, you can see something, but you're not sure if this is cell or not a cell. So bright field images for a long time were considered to be a complete joke, and nobody have been using them in the real science, let's say. So our lab have been one of the people who were actually building a new generation models that would actually be able to work with these very hard and absolutely terrifically bad for any sort of analysis image modality, which is called bright field images. So we were building this kind of UNet models now that were extended, or let's say augmented, to deal with these bright field images. Then if we go to the tissue level, so we were discussing a lot the cell level. If we go to the tissue level, what is happening in many labs of pathology labs around the world is that people that call themselves pathologists, and they don't necessarily just call themselves, they are pathologists. These are the people who study human tissue. So when there is a tumor, potentially a tumor in a person, you take a piece of that tumor, you slice it up, you put it under the microscope, and then you study the image that you get. So this is called digital pathology. And what happens is that as a pathologist, you would normally need to study those potentially gigantic images of tissue, understanding all sorts of visual features, such as the number of cells, the sizes of different subcellular structures, and you have to count them, and you have to compare it to the reference in order to figure out whether a person has or does not have a disease, right? So what we do with AI, again, is that we help the hospitals and pathologists to automate a lot of these analysis, right? So many hours countless hours is spent on things that we know how to deal with from natural objects. We have those models such as YOLO, for example, or many others that are pretty good at counting objects. So now we are the people who are deploying these models such as YOLO and many others into the pathology labs. We work specifically with Estonian pathology labs and specifically in Tallinn, but we also have plans to extend ourselves to Tartu. So, for example, we are detecting something called tubules, counting the cells inside of these tubules, and these are typical features that one needs to assess in order to give a diagnosis. Okay. If we move on to the organ level, right? So we have been at the cellular level, at the tissue level. If we move on to the organ level, then this is something that my company is dealing with. We are working with CT images, so images of computed tomography. This is the person in the cut through. If you cut the, kind of look from inside, this is what you see normally. And what we do as Better Medicine as a company is that we're building diagnostic models that help radiologists. So we are not substituting, no way. We're helping radiologists to make decisions regarding every every other patient that they see. For example, here, I would give that CT scan to my model, and the model would say, all right, I see two kidneys, I see a piece of the liver tissue, I see some pancreas here, and I see a huge pancreatic tumor right in the middle. So this is what we do. We're building these models that help to automate this diagnostic part. So we are the decision support system. We are helping radiologists as a second pair of eyes. So designing intelligent tools to help radiologists. To summarize, so here we are. We go with cellular level, where we detect and count and quantify cells. Then we go into tissue level, where we help to basically automate a lot of these digital pathology processes. And finally, we are at the organ level, where we help to diagnose certain diseases such as cancer by detecting the tumors from the CT scans. All right, so my approach here is that I would like to briefly go through the research that we do on each one of these levels. The only problem is that we have 35 minutes left, and I actually think that I should finish a little bit earlier than 35 minutes, meaning not sharp 8, but give you a little time for questions. So this means that we have not much time left. And one really big problem with me is that I'm easily, let's say, distracted, and I might just go into infinite depth of these discussions. So I'll try to really stick to the schedule, and I'll try to give you the best and the most interesting parts of all of that lecture. All right, so we start with bright field images. So here we are. We're training UNet models, as I said, for bright field images. These are complicated images that look like this. These are pretty tough, low contrast. You can't see much besides some very blurry boundaries here and there. So what we have to do when we were solving a problem of training these models for the bright field images is where to take the ground truth for the models. And the way how we solved the problem was that we used a different modality called fluorescent modality that I showed you even earlier before the bright field images, in order to understand where the nuclei, these are the central parts of the cells, where they are on these bright field images, so that the models could find them by themselves. And this research has had a very good impact in industry. So our models are being deployed in real life. So this is what you can see is the screenshot of the software tool that is usually provided with the microscope that the company called Revity is selling to the biology labs around the world. So besides the microscope, you also get the software tool. And the software tool now has our model as an add-on to it, which is pretty cool. provided that previously bright field images were considered to be a trash. Okay, we didn't stop there. We actually thought of detecting not just the central parts of the cells, which are called nuclei, but also the entire cell, which is basically a cytoplasm. So instead of detecting the central blobs, we set out to detect the entirety of the cell, right? And well, the problematic part of this problem was that many of the cells overlap. So many of the cells like to talk to each other and they reach out to a nearest friend and they overlap in all sorts of ways. And handling this with the current models available for us, it wasn't that possible. So we would have to invent our own segmentation approach in order to handle this. And so we did, with the help of the student, Yaroslav Pritula, has been spearheading this approach. He actually designed a new type of architecture so basically he extended the existing UNet model by adding additional branches that now have been able to, first of all, detect the instances of the cells. So these are the, let's say, these are the instances, these are cells in general. And then for every one of these instances, say what's the mask of this? What is the, let's say, what is the area that this cell is occupying? And then if we multiply one by the other, you get a pretty detailed map, pretty detailed understanding where each exactly cell on the image, right? Including the overlaps. So this has been rather successfully managed by Yaroslav and myself as a supervisor here. Another project that we have been working on was related to applying and somehow taking in external information besides imaging. So all the things I have mentioned to you so far are all somehow related to computer vision problems. So we are solving mostly computer vision problems in biomedical domain, right? But there are lots of data that is not imaging data that can be integrated into the decision-making process, which we call metadata. So you can think about it as, for example, the type of the camera that you're using to make images, or for example, the city in which you were taking these images, and many other things that you know in the background, but you rarely use in practice when you develop these kind of deep learning algorithms. So for microscopy, these are abandoned as well. There are lots of different types of data that you can integrate. For example, magnification factors, cell line type, microscopy type, many other things that you can, in principle, integrate, but it's rarely done. So we have been researching a way to integrate this meta information into the decision-making process and enhance the segmentation quality of our images. And the way how we've done it was through a squeeze-in excitation mechanism. I will very short, I don't want to go into all the details how exactly this works, but in principle, we were able to guide our convolutional models and respect the meta information that we were providing. So we actually saw an actionable difference in the way how the model would perform with and without the meta information. So here you can see on the top row, these are cells, segmentations of cells from the bright field images. The white dashed line is the ground truth locations of those nuclei. And in the middle image, you can see how the model performs when no metadata is available. And on the right, you can see how it does segment cells when it has access to metadata. And you can see that there is quite a substantial difference, and it's also quantitatively present as well. And the lower row, you can see how the model that has been instructed, so it's not been just told, but it's been instructed to segment, let's say, a large tumor. You can see the green dashed line and the green segmentation comparing to medium sized tumor and small sized tumor, right? You can see a drastic change in the way how the model behaves given a different label. So you can as well mislead the model, as well as you can eventually increase the accuracy of the model predictions. So this has been published and is actually available if you want to cite it for some weird reason. Another project that is related to microscopy is related to something called artifacts. These are these kind of weird patches of things. Usually these are like hair or maybe a bacteria colony that have nothing to do with the cells, but can screw up the analysis. So it's usually best practices to detect these things and remove them from the analysis. The only problem is that they're notoriously difficult to detect. For example, these are the outlines of these artifacts, but they're so much more different. So they look very different. And usually these are like huge and weirdly looking objects on the microscopy images. So we developed a whole framework, which we call ScoreCam unit, which integrates something which is called ScoreCam and CAM methods in general. These are class activation maps methods. They are well-known methods that essentially open the black box of the neural networks and show you where exactly the object of interest for the model is located, right? It's highlighting where the object is. And we were able to get a very decent location information of these artifacts from only using classification labels. So we were not using any pixel level annotations, and we were pretty good at detecting these very notoriously difficult artifacts, which we are very proud of. So this is called ArtSec, and it also was published in Nature Scientific Reports. A pretty good paper. You can check it out. I have a bit more slides on the cellular projects. I hope you forgive me for that. I will soon move on to the tissue level and organ level. A couple of more from the cellular level is that we were trying to build a classifier capable of predicting a certain types of treatment that is applied to bright field images and fluorescent images, so basically to the cells. Again, coming back to the story of the treatments, right? Drugs. So when you make drug, you want to figure out whether cells have reacted or they haven't reacted, because ideally you want to kill the cancer cells, right? So you want to know whether there was any effect from your drug. And the most obvious way how to do it is to just, look at the cells and say, well, they don't look nice, so maybe they did react. But more automated way would be to apply, let's say, a classification model, which says, yeah, it did react. So this is something that we have done here. The pipeline was like this, that you take the segmentation of cells, you know where the cells are, each one of the cells, you go one by one. So you, let's say, focus on one cell, you extract the cell using the bounding box of the cell. Then in the classical pipeline, the way how it's been done before is that you apply some kind of classical algorithm. For example, here we are using Harmony software, which extracts tons of features from every cell that you segment. It says what's the color, what's the diameter, what's the square, the area, roundness, et cetera, and many more features that you can extract in that way. Then you do it for every cell in the image, right? So you do it for all the cells in the image. Then you construct a huge data set of these features times number of cells, and you put it into classical machine learning algorithms such as random forest. Okay. On the opposite side, what you can do instead is you can feed those cells directly into a CNN model that we have built ourselves. And you can compare the difference in terms of how they perform, right? So it turns out that CNNs work much better than this classical pipeline, which obviously everybody would already predict. So this been done quite a long time ago. Now we are using transformers, and now we're also trying Mamba models for instead of the CNN model, but generally the pipeline is like this. Some of the final cell level ideas, and actually this is already in a way stepping into the zone of the tissue analysis, is related to image generation, right? So there is a person, Dmytro Fedorenko, he's a master student at University of Tartu, and he has done a tremendous amount of work related to image generation. So he has built he has actually adopted a framework which is called Vox2Vox. It's an architecture that produces, it takes one volume as an input and produces another type of volume as an output. Here I have bright field images in the left side as an input stack. And what we do with them is that we produce a different type of image modality, which is called phase contrast, which is a lot more like fluorescence, but without fluorophore. So you don't have to use any chemicals, and you don't have to purchase any chemicals. You don't have to pay money. You don't have to wait. You could just do it, let's say, in the computer. We call it in silica. And this architecture, this framework, it consists of two parts. One is called generator, and the other one is called discriminator. And those of you who are in the field, you know that this is basically a GAN model that I'm describing here, and that is true. This is a 3D GAN that generates images of phase contrast from bright field images, and it has worked remarkably, really remarkably. And this slide is a major proof for that, because what I did when I made the slides is that I forgot to leave the labels. Which one is the predicted and which one is the actual ground truth. And every time I look at them, and every time I'm asking myself a question, which one is which, I think at some point I figured out that probably the middle column is the generated images, and the rightmost is the realistic images, the ground truth images. This is, by the way, the rightmost is the fluorescence. So we are comparing phase contrast that we have generated to the fluorescence. Now we have also looked in 3D, and we saw that lots of details of the generated images look exactly like in reality. Sometimes even more. There are even more details than what you have in the reality. We have looked through multiple data sets that seem to have different patterns, but in general, it's very hard to tell apart real fluorescence from what we produce inside the computer, which is quite good. I will not stop there, but here's another work that Dima has been working on, also using Vox2Vox, is deblurring. So there's a special type of cell models. They're called spheroidal models of in this case, these are cysts. And there are also spheroidal models of the tumors. So basically, these are type of things that biologists build to study tumors and cysts in the lab. So instead of just putting them on a dish, they build it in 3D because these structures seem to work better. But the only problem with this approach is that at some point you can't study them, because when you make pictures with a microscope, part of the spheroid gets very, very blurry. So we were testing Vox2Vox approach to deblur the dark side of the spheroid. And well, it has worked quite well. So you can see the original images on the left. What we have done using classical approach to deblur the spheroids is in the middle, and our segmentation is on the right. Again, it's very hard to see the difference. Besides that, classical approach sometimes fails and really filters out some of the cells. Here's another example. Again, we see a lot more detail. A lot more cells are visible, and generally seems that the quality has gone up. These are now tumors. So in tumor models, it's a lot worse. The problem is a lot worse because the spheroids are not empty, not the hollow inside, but they're filled with all the other cells. So it's much harder to see through. I will quickly go through these because they're going into detail. And I want to go into tissue because I know we have not much time left. So I want to cover the rest of the organ-related stuff. With the tissue level research, the worst part is the scale of the massiveness of the problem. Imagine that you're looking at the image that has like thousands of these little dots. So this is a small cutout. That what I show on the slide is a little cutout, but in reality, it's a lot bigger. and these small dots are like they're massive number of them. And if you want to build a good ground truth for your models, such as YOLO, then you have to really annotate each one of these demi circles, which is extremely hard and very time consuming. So what happens normally in this field of tissue analysis is that we don't get a very good ground truth. We have only some part of the cells which were annotated and not really all of the cells. This causes algorithm to get confused and underpredict or overpredict certain types of cells. So what we would like to have is not this type of annotation, but that type of annotation. But in reality, it does not work like this. In reality, we have test images, we have the model that was trained on these incomplete annotations, and what we would like to do is we would like to predict the full, massive, fully covered, fully annotated image, right? And the way how we have approached this problem is by introducing a new loss for the YOLO model, which is called generalized background recalibration loss. In a nutshell, what it says is that every time the model is predicting the false positive, we are saying a good model. If it's very confident false positive, so if the model is predicting very confident false positive, we are saying, hey, great job. If it's predicting very unconfidently false positive, then the same loss is striking in. And that if you train the model in this kind of way with this slightly shifted value mapping of the values, then you get much better performance. And this can be illustrated on the right-hand side with GBRL model. And you can see that there are a lot more annotations comparing to the baseline model looking at the ground truth. Okay, moving on because we have 15 minutes left essentially. With Better Medicine, we are working on a organ level, right? And actually, in Better Medicine, we are taking a full body approach, meaning that we would like to build AI models that analyze all organs inside the human. So when we are talking about CT scan, we would like to analyze all of the organs in abdominal cavity, which is basically everything that is covered by the CT scan from the neck to the hip. Okay. At the moment, we have 4 models in making. We have lung and kidney models. We have liver and pancreas. Liver and pancreas are in the proof of concept stage, and lung and kidney has actually finished the clinical study, clinical trial. So we know that kidney model is good. We are actually certifying the kidney model as we speak. And the lung model is about to enter its own clinical trial and get certified as well. This is what it says on this slide here. So more specifically, what is happening is that we have with the kidney model is that we have the CT scan that we segmented to 3 classes. It's kidney, cyst, and a tumor. So it's a 3-class, or you can say 4-class segmentation problem because you also have background as a 4th class. And we are trying to get these as accurate as possible. And we actually ran a full-blown clinical study to show that the model actually works. I was an architect. I was the person who planned and designed the study. So you can see the design of the study on the slide. We have had a very fancy crossed random with the washout period design with a lot of certification and randomness involved. So it's what was kind of trying to be bulletproof in terms of biases. And at the end of the day, another big thing that we wanted to show is that you can, using these models and these architectures, show a dynamic of the tumor development. So when you have person coming in, let's say last year, having a scan, and then you seeing the kidney cancer, and then they come, let's say recently they made a new scan, and then what you do is you run the model, you compare these models, you compare the predictions of these models, and then you assess the volume of the difference, and then you make a decision whether the treatment that you have administered to a person if it has worked or didn't. So not everything in the field is treated by a surgery. So it might have been some kind of chemotherapy, some other type of therapy, and if the size of the lesion of the tumor has shrunk, then it's a good sign, and maybe you should continue having the same treatment, right? So this is the point of all these kind of segmentation models, is that you can quantify the change over time. Now, we are also pushing ourselves into the lung cancer screening. So we would like to build a model that can help radiologists, existing radiology force, by automating parts of their work to enable lung cancer screening. So, for example, the problem is that the cancer incidence is on the rise. There are a lot more cancers these days. Doctors are overloaded. Screening usually requires double the number of radiologists from the normal workflows. And there are fewer and fewer radiologists because of the aging and because of other problems related to all sorts of economical issues. So what we want to do is we want to really launch the lung cancer screening. We would like to detect all the nodules. So we are not only able to detect all the nodules, but what we're supposed to do as a part of the lung cancer screening is that we are supposed to also characterize every nodule. So we have to say that, all right, this nodule is of that type and it's located here, and the margins are this, and it's of a very specifically dangerous nature. And we have to provide this characteristic for every nodule that we see in the CT scan. So essentially, this is the multi-module and multi-level approach that we are taking here. We are detecting the objects, then we are segmenting the objects, and then we are characterizing the objects, so we can provide a very informative decisions to the radiologist that can finalize it and decide on the treatment options for the patient. All right, this is a short summary of what we've been through. Again, there are lots of things that people with computer science background can do in biomedicine, in biomedical imaging. More specifically, it is in the cellular level by building models that can detect cells, that can quantify cells. This has been massively popular around the labs in the world. We are constantly talking to many actors in many universities and many labs that do need this sort of analysis. On the tissue level, we help pathology labs to automate and get rid of tons of very complicated manual work that they perform right now by hand. And we believe that many of the systems that we know how they work, like YOLO, for example, they're not that, they're not that somehow extraterrestrial, but they would help and save a lot of our hours from these pathology doctors. And finally, on the organ level, we help to detect and measure and classify as well, because sometimes you have to make a decision whether the volume, whether the lesion that you have identified, whether it's a malignant lesion or is it a benign lesion. So we are helping with these type of decisions as well. This is basically a short summary. I just wanted to say, before we go on to maybe questions and we have a bit of a discussion, which I hope we will, I just wanted to say a big thank you to my research group. This is the one that's been dealing a lot with a cellular research, and my company. So these are the guys who are behind the AI models for cancer detection, for cancer diagnostics. And finally, I just wanted to remind you that there is additional donation channel that you can use by supporting a very good person and my PhD student father, and that would be really much appreciated. I will leave my full screen mode so that you guys can ask questions and I can see what is maybe if there is any discussion here. And Timur is back.
Yeah, we already got some questions. So first question is from Ivan. You already mentioned during your lecture that you used YOLO models, but overall, our medical models usually trained from scratch. Seems like most pre-trained models are absolutely useless for this domain.
Yeah, so this has been a very long, at some point, very long discussion whether pre-training works. Pre-training, I mean, on a natural object such as ImageNet, obviously, we're talking about here. It does work. It does massively help. And almost all the models that we are using, almost, what I'm saying almost is that sometimes there are just no models that come pre-trained for some type of things that we do. But generally, we try to deal with the pre-trained models because they do help in classification, segmentation, object detection, almost all over the place. The thing is, these first layers are still useful for all sorts of things. So yeah, I understand where the question is coming from because it's such a different thing, but it turns out that the first layers are still quite useful for the things we're discussing here.
Yeah, so you are not using for the full pipeline some pre-trained models, but for some layers of its pipeline, you're using them, right?
So we at some point, very early on, we tried to freeze the layers. We tried to freeze the early layers and only retrain the later layers. But I think very soon we learned that retraining the entire model makes sense. Even the first layers still become more, let's say, specialized to the things that we are working on. But it's you can think about it as having a head start, albeit you have a little bit moved in a slightly different direction. So you have to go back to the main road and drive a little bit ahead, and then you hit the target, right? So it's like if you think about the loss layout and optimization problem, it's still a step in the right direction. So yeah, we retrained the full model actually.
Okay, got it. And if it is not a secret, do you use something else that you can mention besides YOLO?
Yeah, we use UNet a lot. We have built our own extensions to the UNet. So the student I mentioned, they actually added several branches, and they have been able to convince UNet to do instance segmentation. So this is something that we're about to publish because UNet out of the box does not provide the instance segmentation. This is something we can claim a little bit of credit for ourselves. We have used basically in the cellular world, we have also used a lot of transformers. So VIT, SWINs, we have used SEM, which is a famous model that says segment anything model. If you guys heard about it, there is a MedSem, there is a MicroSem. I can continue working like basically everything you can find in the literature we have used in one way or the other.
Okay, got it. Thank you. And
I think UNet and YOLO are the main horsemen of the apocalypse here. So they are the main characters in this play.
Okay, noted. Thank you. And another question from Anastasia. Where did you take training data sets, if mostly all medical?
That's a $100 question. It's like $1 million question because Anastasia probably has a point in a way that all the medical data is highly protected. It's a super secure field. Regardless, nevertheless, there are a decent number of publicly available data sets that you can have access to. If you guys have any all sorts of ideas that you would like to try, there is a website called Cancer Imaging Archive. I could drop a link maybe at some point, but basically it's a Cancer Imaging Archive. It's a huge collection of publicly available data with different licensing. The problem is that if you are working as a company, you have to be really on the lookout for the different types of licenses that these data sets come with. Some of them come with commercially prohibitive licenses that you can't use for any commercial products. You should be really aware of that. But if you are, as myself, you can step into this academia role and you can say, well, I'm just doing research here. Then there are lots of data sets that you can use. For microscopy images data sets, there are fewer, but still you can find some. And also we do a lot of data annotation ourselves. So we actually build our own data sets. We're trying to make them publicly available to help progress the field. So because that's the way, yeah.
Okay, got it. Thanks. And we have two questions that are really similar.
About
From
synthetic
Tony.
data.
Yeah, what about synthetic data for medical
Absolutely.
purposes? And
Absolutely, yeah. Absolutely, guys. These are great questions. I have right now, I have at least 3 different projects where we simulate a lot of data. First of all, it has been we have seen it helping massively in training our models. It's just terrifically helping. The thing is, if you develop your generators, synthetic generators, such that first they produce realistic data, but secondly, you can control the data that they produce in a way that you can move things around and you can shuffle things, you can change their sizes. So you do conditional generation, not just any type of generation, but the conditional generation. This have had massive effect on helping to build segmentation models, detection models, etc., etc., etc. Right now, one of my students is building a stable diffusion model for generating CT scans with the fake kidney cancers and hoping that this will help to build better segmentation models. I can see right away Anastasia's next question was what your YOLO model exactly use for those tasks. The YOLO was specifically trained to detect those little dark spots as you see on the tissue. These are cells, so these are nuclei actually of the cells. And the thing is, you have to count the number of cells in order to make a diagnosis, because if there are many dividing cells, this usually is a sign of the cancer, because cancer is a type of very active tissue that constantly divides. And if it's constantly dividing, the number of cells that it usually exhibits in the same volume is much larger than you would expect in normal tissue. So that's why you need to count cells, and YOLO has been specifically trained to count the cells.
okay.
Ooh.
Yeah, I think we don't have any other questions as for now from our viewers. But I also wanted to ask about can you give any recommendation for computer scientists if they are willing to switch or get into the field of biomedical imaging or biomedical AI? Something they should focus on, maybe to get some domain specific knowledge, or it is not that important and
Yeah,
learn
absolutely.
something else?
Absolutely. First of all, I think you guys, those of you who come from computer science background, who work in IT companies, who deal with machine learning on a daily basis, or maybe data science pipelines on a daily basis, you can be on the lookout for public competitions that deal with the medical images. There are websites like Kaggle, which I'm pretty sure all of you know about, but there are others like Dream4 competition, the Dreamforce Life, and these kind of things, which offer competitions in this area, which does not normally end up in Kaggle. So you can find a lot of these competitions that are relevant to the field, that you can get a glimpse, you can get the feeling, how does it feel like to develop these models for these kind of applications. But also, maybe you should be on the lookout for companies like Better Medicine that offer jobs in this area, because we have had all our AI engineers basically come from all these different fields, and when they come, they say, guys, I was really looking for a purpose, you're giving us purpose. I think these kind of things indeed give purpose. So yeah, I'm pretty sure you'll find something, but you can start off with the competitions and university programs. These are also nice. I see the last question here from Artem Bachinsky is actually, hi Artem, I'm glad to see you here. Type 1, type 2 errors in your project. This is a very tough question, because you normally don't want to have either. It really depends on which. So for those of you guys who don't know, the type 1, type 2 error, which Artem is referring to, these are called false positives, the type 1 error, and false negatives, these are called type 2 error, just to be on the same page. But eventually, these are both bad. The type 1 error, a false positive, is when you say that the person has cancer, but they don't in reality. right? And the type 2 error is when you say, no, you're healthy, but you are not. You actually have cancer, right? So both are evil, but the more evil they are, and depending on the circumstances. So if you're running a screening program means that you are screening hundreds of thousands of patients. And what you surely don't want to deal with is an influx of tons of patients that do not have cancer, but they've been told that they have cancer. And by the way, people do commit suicide if you tell them they have cancer. So this is a very serious issue. You don't want to deal with that. So what it means is that you don't want to overcall cancer patients. So you don't want to have high false positive rates here. So type 1 error is pretty bad in the screening cases. When you're dealing with the more specific cases, when a patient has been referred to by a specialist, right? So there's a patient, they have very specific symptoms, and here you really want to avoid type 2 errors. So you want to have as high sensitivity as you can possibly imagine. So you want to get as many of them diagnosed as you can. So you see that it really depends on the circumstances, but both of these types are pretty evil.
And how do you deal with them if you like get feedback that you of course in this machine learning data science field we will never get 100% of accuracy, so how do you deal with when those things happen?
This is a good question. So there are several sides of the answer. One is the official answer, and the other one is what it actually happens. The official answer is that you have your risk management model where you show that this sensitivity and this specificity is sufficient, and you show that you mitigate the remaining risk by some additional actions, like you're somehow alerting the radiologist that this might be a mistake, that they should choose to test it again or something like this. So basically, you convince the regulatory authorities that I'm prepared to deal with the remaining error, right? And what really happens besides that, but this is also true, but what in principle, what we see happening is that we are running clinical studies that show that radiologists become more accurate using our model than they are when they don't. So, for example, the kidney study that I mentioned in my talk, it has been completed. And we know, for the matter of fact, that radiologists do detect higher sensitivity. So they do have higher sensitivity when they work with our models comparing to when they work alone. So this is how you empirically validate these ideas, and this is how you say, well, here I deal with the type 1 error. Right. There is a Dmytro asking, have you been in a situation one of the segmentation models you developed predicted the person had tumor, but then they were notified on that, but it turned out to be was actually cyst? No, we have not been in that situation. First of all, because we are not yet in the clinical practice, so we haven't been completely in the radiologist's hands, besides the clinical trials and many test runs and stuff like that. So we haven't been yet in the market. We were not allowed to be sold yet because we don't have CE certification. It's a long process. We are about to complete it, but we haven't been there. In these kind of cases, these might happen. We are the decision support system, meaning that the final responsible is a doctor, is a radiologist behind the computer. So they are the ones to take the full responsibility. They are guided, they are supported, but they are not, let's say, they are not taking off their responsibility. So yes, we will be notified. We will take this case in. We will retrain the model. But if you're asking about legal responsibility, then the legal responsibility is in the hospital.
Thank you for the answer. And by the way, it makes total sense that radiologist becomes more accurate because with your solution they are getting something like or additional layer of confirmation that they saw, or instant feedback, and
we basically say that it's like working with your younger assistant. It's somebody who has pre-done the work and you're just checking on them. Sometimes they make mistakes, but you have to be on the lookout and you have to be able to really correct these mistakes. So sure.
Yeah, it is great. And I don't see any new questions. So do you have anything else that you wanted to share or spread the word on?
No, I think this is what I wanted to talk about. Maybe I skipped some parts that just didn't want to have very dry slides with a lot of research on it. But I just wanted to say a big thank you guys for inviting me here, and generally a big pleasure. And thank you all for questions. And yeah, hopefully we can see each other again at some point.
Yeah, thank you too. You did a great lecture. I can say that it was dry. It was quite informative and interesting. And thank you for joining us. And again, congratulations on your birthday. As a final word, I'll say again that I will show you a QR code. And if you can, please support Reactive Post, and also take attention to the funds that also Dima raised up for the father of his student. It is also very important thing. I'll show this QR code too for some time.
Thank you, Tony, and thank you all.
Yeah, thank you all, and bye. So hope to see you in the next season.
Bye-bye. Thank you, Timur.
Bye.
It was nice to meet you. Bye-bye.
Me too.